forget just piling on more data or building bigger computers for a moment. What if the real key to making AI smarter, maybe even faster, isn't just about mimicry, but about understanding, well, the fundamental laws of the universe? Physics, basically.
Yeah, exactly.
Today, we're taking a deep dive into this really fascinating world where physics meets artificial intelligence, and we're going to be guided by the incredible work of Dr. Rose Yu.
What's really striking, I think, is how taking our basic understanding of the physical world, things we learn in physics, can actually unlock completely new abilities in AI. We're moving beyond just recognizing patterns. It's about truly understanding and predicting dynamic systems, and with surprising rigor.
Okay, so our mission for this deep dive is to explain exactly how Dr. Yu is using these physics principles to, well, revolutionize deep learning systems.
And the applications are really tangible. We're talking about predicting your daily commute, understanding massive tropical cyclones.
Right. And you'll also hear about her really grand vision for something she calls an AI scientist, a kind of digital partner for human researchers. So this deep dive, it's your shortcut to getting your head around this cutting-edge field, and honestly, it's pretty surprising implications. So how do you even start connecting something like deep learning with, say, fluid dynamics? It seems like a big leap.
It does.
Well, let's start with Dr. Rose Yu's origin story. It's pretty interesting. Imagine being 10 years old, you get a computer in China, maybe 25 years ago.
Wow, yeah. That would have been incredibly rare back then.
Totally. And that was Rose Yu's start. But she wasn't just, playing games. By middle school, she was already winning awards for web design.
So really leaning into the tech early on.
Exactly. This early curiosity just propelled her. She went from Zhejiang University, majoring in computer science, all the way to getting her doctorate from the University of Southern California in 2017. And she even got an award for the best dissertation there. And just recently, actually, earlier this year, she received a Presidential Early Career Award from President Joe Biden.
Okay, so connecting this to the bigger picture.
Mm-hmm.
Her background isn't just about, technical chops,
Well,
right? It shows this pattern of really innovative thinking, always pushing the boundaries in computer science.
yeah.
And that seems like it prepared her perfectly for this next step, integrating physics into AI, not just building new techniques, but applying them to these really complex real-world problems.
She's now an associate professor at UC San Diego, University of California, San Diego, and really a leading voice in this field they call physics-guided deep learning.
Right.
So what does this actually mean for, our daily lives? Well, for Dr. Yu, it kind of started with something very relatable, LA traffic.
Yes, the classic LA problem.
Exactly. Back in 2016, as a grad student near that infamous I-10 and I-110 intersection, well, she spent a lot of time stuck in traffic. And she started wondering, could deep learning, which back then was often focused on static things like classifying images, could it actually help with things that are constantly changing, like traffic flow?
That's a really interesting conceptual leap for AI at that time, because you have to ask, how do you even start to model something as chaotic, as dynamic as traffic flow using AI, especially when, like you said, most deep learning was looking at fixed patterns?
Her approach was, well, pretty novel. First, she thought about traffic not just as individual cars, but more like a physical process, like diffusion.
Diffusion,
Yeah, think of dropping ink into water and watching it spread out, disperse.
Mhm.
She saw the flow of traffic over roads, kind of like the flow of fluids over a surface. It's governed by similar principles, fluid dynamics.
Okay, interesting analogy.
But her main innovation, the really clever part, was thinking about traffic as a graph. From graph theory in math.
Right, nodes and edges.
Exactly.
Uh-huh.
The sensors on the highways monitoring traffic, those are the nodes, and the roads connecting them, the distances, those are the edges.
Ah, I see. So you create a network map.
Precisely. And this let her create these snapshots of the entire load network every 5 minutes. So you get this dynamic, evolving picture of how traffic is actually behaving moment to moment.
Okay, that makes sense. But the big challenge with deep learning is always data, right? You need massive amounts to train these networks effectively.
True. But luckily for her, her advisor at USC, Cyrus Shahabi, had actually spent years collecting tons of LA traffic data.
Ah, perfect timing. A ready-made data set.
Exactly. It gave her the perfect test bed to train her neural network and really, kick the tires on this physics-guided approach.
And did it work?
Did it ever? Here's the kicker. Their forecasts were reliable for a full hour into the future.
An hour. That's
Yeah.
That's huge compared to what was possible before.
Yeah, it was a massive improvement. Previous models could only manage about 15 minutes reliably.
Wow.
And get this, her team's code was so effective, Google Maps actually deployed it in 2018.
No kidding. Deployed by Google. That's fantastic.
Yeah. And soon after, she got invited to be a visiting researcher there. It's just really impressive to see, fundamental physics directly making something like our daily commute better.
Absolutely. That's a great example of research hitting the real world.
But that success with traffic, well, that was really just the beginning for her.
Yeah.
It led her to tackle another absolutely massive, complex problem: climate modeling.
Okay, from traffic jams to climate change, that's quite a jump.
It is. In 2018, after she gave a talk at Lawrence Berkeley National Laboratory, she started collaborating with scientists there, their focus, predicting the evolution of something called turbulent flow.
Ah, turbulence.
Which is apparently a key factor in climate models, but also a major area of uncertainty.
And turbulence is, well, it's everywhere, isn't it? It's fascinating how pervasive it is.
Like where?
Well, think about milk swirling in your coffee, or smoke curling up from a chimney, or even those huge ocean currents, eddies that span thousands of miles. That's all turbulence.
Huh.
And predicting it with traditional methods, like trying to solve the Navier-Stokes equations, which are basically the super complex math rules for how fluids behave, is just incredibly slow, computationally very, very intensive.
Right.
And that's precisely why we struggle to predict things like hurricanes and tropical cyclones accurately. The turbulence is a huge part of the puzzle, and it's hard to calculate fast enough.
Okay, so how does AI help speed this whole thing up?
Well, her team essentially trains deep neural networks using the best available numerical simulations of turbulence. They feed the simulation data to the AI.
So the AI learns from the simulations.
Exactly. The networks learn to recognize the properties and patterns hidden in that data. They learn to sort of emulate the simulation,
Right.
but without having to do all those incredibly time-consuming brute force calculations step by step.
So it's like teaching the AI to get the gist of it, the intuition, rather than calculating every single detail.
That's a good way to put it. It learns the underlying dynamics and the performance gains. They're really astonishing.
How astonishing.
This approach speeds up the predictions by a factor of 20 in 2D settings.
Okay.
Pretty good. But in 3D settings, it's an incredible factor of 1,000 times faster.
1,000 times, seriously.
Seriously, 1,000 times faster. So imagine having a turbulence prediction module built with this AI that you could just slot into larger climate models.
That would completely change the game for hurricane predictions, wouldn't it? Maybe even long-term climate forecasts.
Potentially, yes. It can lead to far more accurate predictions. It's a really exciting prospect.
It's amazing how widely this idea of turbulent flow applies. You mentioned coffee and oceans, but where else does it pop up?
Oh, it's practically everywhere, like you
That's
said. Think about blood flow in our bodies. Turbulence there can actually contribute to things like strokes or heart attacks.
Wow, okay. Didn't think of that.
Yeah. Or stabilizing drones. That was part of her postdoc work at Caltech, actually.
Drones. How does turbulence affect drones?
Well, when drones take off or land close to the ground, the airflow from the propellers interacts with the surface. It creates turbulence, which can make the drone wobble or become unstable.
Ah, okay.
So her team used a neural network, guided by physics principles, to model this specific turbulence. And that led to better control systems for the drones.
Wow, that's clever.
And even in something as extreme as fusion power.
Fusion power, like trying to build a star on Earth.
Exactly. Controlling that super hot plasma, we're talking 100 million degrees, involves understanding its internal turbulence. Her team is actually working on that now, developing a deep learning model to predict the plasma's behavior almost instantaneously, like in a split second.
That's incredible. The range is just mind-boggling, from traffic to fusion.
It really shows the power of applying these fundamental physics principles through AI.
Okay, now let's shift gears a bit and explore her really audacious vision for the future of scientific discovery itself. Dr. Yu envisions something she calls AI scientist.
AI scientist.
Yeah.
Sounds ambitious.
It does. She sees it as a suite of, digital lab assistants that she believes could fundamentally change how we even make scientific breakthroughs.
Okay, so where did an idea like AI scientist actually come from? What was the spark?
Well, apparently over the past couple of years, her group developed some AI algorithms that could do something pretty remarkable. They could automatically discover symmetry principles just from looking at data.
Discover symmetries, like,
For instance, their algorithm identified the Lorentz symmetry, the cornerstone of Einstein's special relativity,
right,
about how space and time are linked.
right, constancy, the speed of light, etc.
Yeah.
It found that from data.
Yeah. And it also found rotational symmetry, like how a sphere looks the same no matter how you spin it. And the key thing is, it wasn't specifically trained to know these things, it discovered them.
Okay, discovering known physics is impressive validation, but the implication is.
Exactly. While those symmetries were already known, the crucial point is the capability it demonstrated, the potential to discover new, currently unknown symmetries.
That would be absolutely monumental for physics, a game changer.
Totally. And this capability seems to be what really laid the foundation for this whole AI scientist concept.
Okay, so what is this AI scientist in practice? Is it just one giant neural network?
No, not exactly. She describes it more as an ensemble, a collection of specialized computer programs working together.
Ah, okay. Like a toolkit?
Sort of. Her group has already built algorithms that can help with specific individual tasks. Things like refining weather forecasts or identifying the key factors driving global temperature rise.
Hmm, causal factors too.
Yeah, even uncovering causal relationships, like they looked at the effects of different vaccination policies on how diseases spread.
Okay, so they're building these specialized tools. What's the bigger picture then?
Well, connecting this to the bigger picture, they are working on building a broader foundation model, like the large language models we hear about.
Right, trained on massive, diverse data sets.
Exactly. But this one would be designed to be versatile enough to handle all sorts of scientific data types, numbers, text, images, videos, information coming from all kinds of different scientific instruments.
That's ambitious, a multimodal scientific foundation model.
Yeah, they apparently have an early prototype already, and she expects it to become much more comprehensive, much more intelligent, within just a couple of years.
Wow. So how does she see this actually being used day to day by scientists?
She imagines it assisting in, well, practically every step of the scientific discovery process.
Every step.
Think about just the literature survey stage.
Hmm.
You know how researchers spend ages gathering and reading papers?
Oh, yeah. It's a huge time sink.
Imagine a large language model component of this AI scientist reading and summarizing, say, thousands of relevant research papers while you're having lunch.
Okay, that would certainly speed things up, free up a lot of time.
But there are limits, right? What is AI not good at in this vision?
Right. And this is a critical distinction she makes. AI, even this AI scientist, is not good at judging scientific validity in the way a human expert does. It just can't compete with an experienced researcher's judgment, their intuition, their critical assessment.
So it's not making the final calls.
Exactly. While it can definitely help with things like generating hypotheses, maybe suggesting experimental designs, analyzing complex data, it can't currently, go into the lab and actually carry out sophisticated experiments itself.
Okay, that's reassuring. So the goal isn't to replace human scientists.
No, absolutely not. And she's very clear about this. Her vision for AI scientists is really about partnership. It's designed to relieve researchers of some of the drudgery, the tedious parts of science.
Letting people focus on the creative stuff.
Precisely. Letting humans handle the truly creative and critical aspects, which, let's be honest, we're still uniquely good at. She explicitly says she doesn't envision, and actually wouldn't ever want to see, a machine substituting for or interfering with human creativity.
Okay, that's a really important point. It's about augmentation, not replacement.
That seems to be the core idea.
So Dr. Yu's work clearly presents this unique, really powerful path for AI development, grounding it in physics. But how does this physics-guided approach kind of fit into the broader AI landscape, the one we see dominating the headlines, often filled with hype?
Yeah, that's a great question.
I mean, how does it stack up when we compare it to the massive investments, the rapid-fire advancements happening elsewhere in AI right now?
It's a really interesting contrast, actually, because while a lot of the big headlines focus on, scaling models to absolutely enormous sizes or building ever more general capabilities, Dr. Yu's work emphasizes something different. It's about a deeper integration of scientific principles.
More rigor.
Exactly. It suggests a path where AI isn't just powerful, but it's also rigorous and maybe even more interpretable, precisely because it's grounded in these fundamental laws of physics. It understands the why, not just the what.
Right, because you see headlines constantly, don't you, about this intense competition. Major tech leaders, like Mark Zuckerberg, leading these huge hiring
Oh
blitzes,
yeah, the talent war is fierce.
offering top AI researchers just eye-watering salaries, endless computing power, trying to build these super intelligence teams, poaching people left and right from places like OpenAI, Google.
hmm Billions are being poured into scaling up.
And then there's all the talk about AI's impact on jobs. You hear things like vibe coding potentially coming for engineering jobs.
Right, where AI just generates code based on a description or even just a general idea.
Yeah, and that naturally raises questions about AI's impact on careers we used to think were pretty stable.
And that scaling approach also brings up other concerns, like the sheer energy consumption of these massive models. That's becoming a significant issue, often kind of hidden.
True, the environmental footprint. Dr. Yu's approach, being more efficient because it understands the physics, might actually offer an advantage there too, maybe.
It could, potentially.
Hmm.
If you don't need brute force calculation because the AI understands the underlying principles, it might require less computation, less energy. That's definitely a possibility worth exploring.
And then, of course, there's the elephant in the room. AGI, artificial general intelligence.
The big one.
This theoretical idea of an AI that can understand, learn, apply intelligence across basically any task, just like a human. You see the partnerships like OpenAI and Microsoft kind of hinging on defining what AGI even means.
Right.
And you see research, like from MIT, developing models that supposedly never stop learning, always improving. It all fuels this ongoing conversation about, the next giant breakthrough, AI agents handling complex stuff like booking your dinner or changing your flights automatically.
It's fascinating to think about how Dr. Yu's physics-guided approach might actually contribute to something like AGI, though. Not just through sheer scale or processing power, but by enabling AI to actually reason with fundamental principles, maybe even discover new ones.
Making it genuinely intelligent in a scientific sense, not just a really sophisticated pattern matcher.
Exactly. It's a different flavor of intelligence, perhaps one grounded more in understanding the world's rules.
So, wrapping things up, you've heard how Dr. Rose Yu's journey, starting from that childhood computer gift, led her to this really groundbreaking work, applying the immutable laws of physics to make AI faster, smarter, more reliable.
From predicting your commute.
Understanding hurricanes, yeah.
And this deep dive has really shown us, I think, that the future of AI isn't just about bigger models or more data lakes. It's also critically about achieving a deeper, more principled understanding.
And sometimes the path to that understanding is found by looking towards established scientific fields, like physics.
Absolutely. Leveraging centuries of human knowledge.
And she's not just building tools, is she? She's really fostering this idea of partnership between humans and AI in science, aiming to relieve the drudgery, take away the tedious bits.
While preserving, and maybe even enhancing, the crucial human element of creativity and critical judgment.
Right? So here's a final thought to leave you with. As AI continues to evolve at this just breakneck speed, integrating into pretty much every facet of our lives, maybe the most profound insights, the truly game-changing breakthroughs, won't come just from trying to simulate human intelligence. Maybe they come from truly understanding the fundamental physics of the universe itself.
That's an interesting thought.
What new discoveries, what new capabilities could emerge if more AI development started following this kind of physics-guided path? Something to ponder.